What is the difference between brittle and ductile fracture? Imagine a metal rod under stress. Will it bend and stretch before breaking, or snap suddenly like glass? The way materials fail reveals a lot about their internal structure and behavior. Today, we're exploring the key differences between brittle and ductile fracture, two main ways materials break apart. Understanding these can help us prevent failures in everything from bridges to airplanes. Ductile fracture happens when a material undergoes a lot of plastic deformation before it finally breaks. Plastic deformation means the material changes shape permanently, like a piece of metal stretching or necking down at the fracture point. When a ductile material fails, it absorbs a lot of energy, which means it takes a lot of force over time. You often see a rough, fibrous surface on the broken part, and the crack grows slowly, giving some warning signs like visible deformation or stretching. Metals like copper or aluminum tend to fracture ductilely, especially when they are warm or under moderate stress. This type of failure is usually preferred because it shows signs of damage early, giving time to fix or replace the part. Brittle fracture, on the other hand, happens suddenly with very little plastic deformation. The material snaps quickly, often with a sharp, shiny, flat surface that looks like a clean cut. The crack spreads rapidly, sometimes almost as fast as sound travels through the material. Brittle failure usually starts at stress concentrators like notches, cracks, or flaws that are present from manufacturing or design. Materials like glass, ceramics, and some metals under cold conditions tend to fracture brittly. Because brittle failure occurs so fast and with little warning, it can cause catastrophic damage without any visible signs beforehand. The main differences are how they behave before breaking. Ductile fractures show lots of deformation and absorb high energy, while brittle fractures happen with almost no warning and low energy absorption. The surface of a ductile fracture looks rough and fibrous, whereas a brittle fracture appears flat and shiny. Crack growth in ductile failure is slow and detectable, but in brittle failure, it is rapid and often unpredictable. These differences are important for engineers because choosing the right material and design can prevent sudden failures. For example, in safety-critical parts like airplane wings or pressure vessels, ductility is often favored to give warning signs before failure. Analyzing how a part broke, whether it was brittle or ductile, helps engineers improve future designs and avoid dangerous surprises. Brittle failure is often linked to stress concentrations, material flaws, or low temperatures that make materials less ductile. These factors allow cracks to form easily and spread quickly. Ductile failure involves plastic deformation that redistributes stress and slows crack growth, giving warning signs. Understanding these failure modes helps us design safer, more reliable products by selecting materials that resist brittle fracture and controlling manufacturing processes to minimize flaws.